Okay, we have to finish this example in section 9.9. This was number 24. So this is where we left off. Let me go back to the beginning quickly and explain what we were doing. So we were given this function 1 over 1 plus x, and we were told that the power series representation for this function was the sum n is 0 to infinity of minus x to the n. Remember where this is coming from. Think of this as the sum of a geometric series a over 1 minus r. So there's a geometric series where a is 1 and r is minus x, because it's 1 minus minus x. That's where so the a is 1, the r is minus x. And again, you can rewrite this. You can break the negative x up as negative 1 to the n, x to the n. That's where that comes from. Well, since r is negative x, remember geometric series converges when the absolute value of r is less than 1. So the absolute value of negative x is just absolute value of x. And we need that to be less than 1. But if the absolute value of x is strictly less than 1, x is between negative 1 and 1. So that's the interval of convergence for this series. Same thing here. 1 over 1 minus x, a is 1, r is x. Okay, we wrote this in this form because a is 1 and r is x, so it's a geometric series. And when does a geometric series converge? When the absolute value of r is less than 1. Here r is x. The absolute value of x less than 1 gives you the interval of convergence negative 1 to 1, just like the first one. Okay, so then the question was, consider the function f of x as natural log of 1 minus x squared. Okay. Notice this doesn't look like the examples we did in class where it was, you could write it in a over 1 minus r form. You're not going to get that. But they told you that this function is equal to the integral of 1 over 1 plus x minus the integral of 1 over 1 minus x. And we sort of checked that to see that that made sense. Okay, so we're trying to find a power series representation for this function x. So we need power series. So let's replace 1 over 1 plus x with its power series right here. So we replace 1 over 1 plus x with its power series. And here we replace 1 over 1 minus x with its power series coming from here. Okay, now we have the integral of a sum. That's just the sum of the integrals. So just integrate term by term. And that's what we did going to here. So negative 1 to the n is a constant, bring it down. The integral of x to the n is x to the n plus 1 over n plus 1. Same thing here, right? The sum of x to the n, the integral of that is just going to be x to the n plus 1 over n plus 1. And we put the plus c out front, just so if you put the plus c at the end, it may look like it's part of the summand, which it's not. So they put the plus c out front. And then we noticed we have two sums going from n is 0 to infinity, and they're subtracted. So you can combine those into a single summation. And they both have n plus 1, the denominator, so that goes in the denominator. Notice in the numerator, this is negative 1 to the n, x to the n plus 1, and this is just xn plus 1. So when you subtract, both of these terms have an x to the n plus 1, so we factored it out. Factor out x to the n plus 1 from the first term, you get minus 1 to the n. Factored out of the second term, you get 1, but there's a minus here. There's where the minus 1 comes from. Okay, so that's where we stop. Okay, now we want to do some simplifying here. So this is just sort of scratch work to explain where the next step is coming from. Let me just look at this. I'm not worried about the plus c. Let's look at this series for a second. Let's just start plugging in numbers, n equals 0, etc., and see what we get here. Okay. Notice, again, this is just scratch work. When n is 0, we get x to the first over 1, so we're going to have an x term. Now, what's the coefficient? When n is 0, we get negative 1 to 0. That's 1 minus 1, which is 0. We get 0x, which is 0. Now, what about when n is 1? When n is 1, I get a 2. I have an x squared over 2. And when n is 1, we get negative 1 to the first, minus 1 is negative 2. What about when n is 2? Well, let me just jump to here. When n is 2, you get negative 1 squared, which is 1. 1 minus 1 is 0. So you get another 0. And just for kicks, I'll put in the number. That's x cubed over 3. All right, let's do one more. And then when n equals 3, you're going to x to the fourth over 4. And when n is 3, you get negative 1 cubed is negative 1 minus 1 is negative 2. So you see what's happening here. When n is even, we're just going to get a 0. And when n is odd, we get a non-zero term. So there's no point in having this series written in this form Because when you expand, the even terms wind up being 0. It's just kind of a waste. Okay? So what we're going to do here to just get the even terms, but when n is odd, right? We get even powers on x. So we're going to replace n here in the expression with 2n 2n plus 1. You could do 2n minus 1 as well, because that's odd. So, right, this expression turns out to be 0 when n is even, so we want to only consider odd values of n. So if we let n be replace n with 2n plus 1, 2n plus 1 is always odd. All right, so let me do c plus the sum, n equals 0 to infinity. That n we leave alone. But here, we're going to replace n with 2n plus 1. So it's negative 1 to the 2n plus 1 minus 1 x to the 2n plus 1 plus 1, and then divided by 2n plus 1 plus 1. So everywhere they're not in the sum and, but not in the lower limit. In the sum and here, I'm replacing n with 2n plus 1. Right. So let me simplify that. So here we get x to the 2n plus 2 and 2n plus 2 in the denominator. Notice the power on the x is always even and the number on the bottom is always even, which is what we were trying to get here. And if 2n plus 1 is always odd, so negative 1 to the 2n plus 1 is always negative 1. Negative 1 minus negative 1 is negative 2. Okay, we can do one more thing to cancel, to simplify. Notice you can factor a 2 out of the denominator and then cancel it with the 2 in the numerator, so you get negative x to the 2n plus 2 over n plus 1. Again, I factored a 2 out of the denominator and canceled the 2 in the numerator. Okay, so that's what we get. I wouldn't be this tricky on a test or anything. I just want you to be aware that that's what they're going to do in the back of the book. Now, notice if we, just for kicks, so suppose we started expanding with n, like I did before. So notice when n is 0, I get negative x squared over 1. And when n is 1, I get negative x to the 4th over 2. And when n is 0, 1, when n is 2, I get negative x to the 6th over 3. And if you compare with what I had before, when I had the zeros, these were the non-zero terms. Okay, I didn't simplify before, but I didn't cancel, but this is what you get. So we did actually make it so we're not plugging in numbers and getting a 0 anymore. Okay, so there we go. So that's that. Now, I don't need these anymore. Now, remember what this is supposed to represent. This is a power series representation for this function f of x. Now, I know when we put the plus c here, we were doing it because we were integrating and you put the plus c. But remember what that's for. An indefinite integral is a set of all antiderivatives of the integrand. That's why we need the plus c. But that's not really what the plus c is doing here. Remember, this is supposed to be a single function, f. So the way this is written isn't really a true statement, right? This is a single function equal to a difference of definite integrals, which would be an infinite number of functions. So the plus c here is really standing for the constant you need for this to actually equal this one function. Okay, you may remember in Calc 1 you had problems like, suppose f prime of x was, x plus 5, and you were told that f of 1 was 2. So when you found the antiderivative here to get f would be x squared over 2 plus 5x plus some c, right? The c here didn't stand for any c in the world, like in an indefinite integral, right? The c just stood for the constant, because there are a lot of antiderivatives of f, so that's a certain constant you need for this to be true. So you let x be 1, you let y be 2, and you figured out what the c had to be. So that's exactly what we're going to do here. The c is a particular c. Okay? So what do we have? F of x is equal to that. Right? Let me write that again. So f of x is c plus the sum, n is 0 to infinity, of minus x to the 2n plus 2 over n plus 1. Okay. and that's supposed to be natural log of 1 minus x squared. Okay. Okay, so let's plug in x equals 0. This has to be true for all x in the interval of convergence, which we haven't found yet. But in particular, we know that this is a power series centered at 0, so we know this, it always converges at that c value. So let's plug in 0 for x. It's c plus the sum. But what happens when we plug in x equals 0? You're just going to get a bunch of zeros. Right? Because you have 0 to the even power 0, 0. So that's a good reason to plug in 0 here, because although this goes to 0. So notice c is natural log of 1, which is 0. So it turns out we didn't need the c after all. C turns out to be 0 for this particular function. Okay, so c is 0. So my function now is just this. Right? So this is the power series representation of the function natural log of 1 minus x squared. Okay, so that's the first part. Then it says identify the interval of convergence. Okay, now remember, we had a theorem that said if you know the interval of convergence for a particular function, if you differentiate that function, the radius of convergence will be the same. So if you had some function g, and I'm making up something here, centered at 0, and your interval of convergence was -3 to 3, say, and then you looked at g prime, okay, so this is centered at 0, the radius of convergence is the same, so you're going to still be centered at 0 and go 3 either way. So the interval of convergence from -3 to is going to still be from -3 to 3, it's just the endpoints could be different. Same thing if you do the integral of g. It's still going to be from -3 to 3, it's just the endpoints could be different. Okay, so that's nice. Okay, so remember how we got this function. It was the integral of 1 over 1 plus x minus the integral of 1 over 1 minus x. And I mentioned at the beginning, the interval of convergence for each of those was -1 to 1, using the geometric series. All right? So if we integrate that first one, the 1 over 1 plus x, the radius of convergence is still going to be 1, centered at 0. And the integral of 1 over 1 minus x, that is centered at 0, it's going to have the same radius of convergence. So both of those were from -1 to 1, which means the integral of both is going to be -1 to 1. Now what's the only difference here? So I know the interval of convergence of this is going to be -1 to 1. It's just a question of, do we include the endpoints or not? Because when you integrate, you can add in the endpoints. Okay? So all we have to do is check the endpoints here, right? We don't have to reinvent the wheel. You could use ratio test here, do it from scratch, and you get -1 to 1. But we already know it's going to be -1 to 1 because those were the interval. That was the interval of convergence for the two functions we started with before we integrated. Okay, so let's check the endpoint. So what about when x is 1? So f of 1 is the sum of -1 to the 2n plus 2, -1 to the 2n plus 2 over n plus 1. But 1 to the 2n plus 2 is 1 to even any power is 1. So we're just getting the sum of -1 over n plus 1. And what does this series do? Well, it's basically the harmonic series, so this diverges. The series diverges since harmonic. So that right there tells me 1 is not in the interval of convergence, so it's parentheses. Okay, now what about the other endpoint, -1? So let's take f of -1. So this is the sum of -1 to the 2n plus 2. So the negative out here is the negative in the problem, and I'm replacing x with -1. Now what does that turn out to be? -1 to the 2n plus 2. 2n plus 2 is always even. -1 to an even power is 1, and so we're going to get -1 over n plus 1, which is exactly the same series we got there. So by the same reason, which diverges since harmonic. So notice -1 is not included in our interval of convergence, and it's just the open interval -1 to 1, which was the same interval that we had to start with. But when you integrate, we could have added in either one or both of the endpoints in the interval of convergence, so we had to check them separately. So that's the end of that example.